Problem number 2. So a W14 by 90 steel column is used to carry an actual dead load of 600 kN including self-weight and live load of 1,900 kN. The column is 9 meter long and is pinned at the top and bottom in both axes. So for this one, meron tayong pinned connection. Additional support has been added with lateral and torsional bracing about y-axis at midpoint. So let's say ito yung column section natin. So nagkaroon daw tayo ng bracing dito sa y-axis natin. So for this one, meron tayong bracing at this sa y-axis natin at midpoint. Okay. So meaning to say, at 4.5 meter simula sa taas, meron tayong bracing dito sa y-axis natin. So along dito sa y-axis natin, meron tayong bracing. Dito naman sa x-axis, wala tayong makikitang brace dito. So for this one, ito yung brace natin. Siyempre, na-divide yung column natin into 2. So take for 4.5 na lang yung mga length natin with respect to the y-axis. Determine the adequacy of the column section given. So kapag sinabi nating adequacy yung chine-check natin, we are investigating yung column section natin. Therefore, problem number 2 is an investigation problem. So we're going to use NSCP 2015 provisions for ASD and LRFD. So, use Fy is equals to 345 megapascal. So, given yung properties natin, so naka-megapascal tayo, millimeter and mm squared. So, for this one, siyempre, para shortcut na lang tayo, we will going to solve yung nominal capacity natin. Nominal capacity, that is equal to FCR multiplied by EG. Kaso yung FCR natin, magbabago yung value niyan depende dun sa column natin. If it is short or long. Kaso nga lang, bago natin i-compute kung long or short yung column natin, we need to check muna yung compaction. So, we will going to check yung compaction nung section natin with respect to the flange and web. So for this one, unahin muna natin yung flange natin. So hanapin natin yung width to thickness ratio with respect to the flange, which is equal to BF all over 2TF. So yung value ng base of the flange natin, that is 368. While the value of the thickness of the flange, that is 18 mm. So you have a value of width to thickness ratio na 10.222. So kapag flange, always remember that is unstiffened element. Kapag naman web, we are talking about stiffened element naman. So i-compare natin yung nakuha nating width to thickness ratio to the value of your lambda sub RF, which is equal to 0.56 square root of E over Fy. You just need to substitute yung given natin na 345 and the value ng E natin, which is equal to 200 megapascal. So we have a value which is equal to 13.483. So, ipagko-compare natin yung nakuha natin na 10.222 and yung 13.483. Since less than etong width to thickness ng flange natin sa lambda R sub RF, therefore, compact yung flange natin. So, we have a compact flange, therefore, not slender yung element natin. So, kung na-check natin kung not slender yung element natin sa flange, so, lipat naman tayo sa web naman. So when we are talking about web, hahanapin din natin yung width to thickness ratio sa web natin, which is equal to h over tw. Kaso, kunin muna natin yung value ng h natin. So titingin tayo dito sa stiffened element natin, dun sa table natin. We're going to use case 10. So for this one, the value of your h, so yung total depth natin minus 2 k des. So yung d natin, that is equal to 356 minus 2 multiplied by k des, na 33.3. So the value of your h, that is equal to 389.4 mm. So substitute natin dito. So you have 389.4 mm divided by the thickness of the web, which is equal to 11.2. This is 200 pala to. So sorry, this is 289. So 289. So you have a value which is equal to 25.839. Then, ipagko-compare natin yan. Siyempre, kung meron tayong lambda sub RF, so we have lambda sub RW, which is equal to 1.49 square root of E over Fy. So, substitute natin yung E na 200,000 megapascal, Fy 345. So, you will have a value of 35.875. So, pagko-compare natin yung dalawa, so yung nakuha natin dito sa web natin, yung width to thickness ratio na 25.839 versus yung nakuha natin, since less than yung width to thickness ratio natin sa web, therefore, compact web. So, since compact yung web natin, not slender element yung web natin. So, for this one, so wala na tayong masyadong problema dyan. Kasi na-check natin na both compact yung mga elements natin sa flange at saka sa web. So, for this one, kung ganun yung condition na nangyari, we will going to use yung section 505.3 sa NSCP 2015 for flexural buckling of members without slender elements. So, under that section, so without slenderness, so, kukunin natin yung mga values natin sa FCR natin. We will going to determine kung short or long yung column natin. So, first, we're going to solve for the value of your slenderness ratio. Kaso nga lang, we have two values of slenderness ratios natin dito. We have slenderness ratio with respect to X and slenderness ratio with respect to Y naman. For this one, so yung value naman ng slenderness natin, that is KL over R. So yung gagamitin natin dito for our effective length factor natin, so yung gagamitin natin dito is yung mga theoretical value. So we're going to use yung theoretical value ng K natin when we are talking about investigation problem. Therefore, kung ano yung value ng Kx natin, yun yung value ng Ky natin, which is equal to 1.0 kasi nga pinned at the top and bottom. So, let's consider first yung y-axis natin in computing for your slenderness ratio. So, y-axis natin, titingnan natin, nahati siya sa midpoint. So, dito sa y-axis natin, along y, so nahati siya. So, along y, so nahati siya sa dalawa. Meron tayong 4.5 at saka 4.5. So, for this one, so, consider natin value ng L natin dito, that is equal to 4.5. Kasi nga, parehas lang naman yung value ng length natin. Kasi, brace at midspan tayo. Brace at midpoint. Siyempre, na-divide lang sa dalawa yung 9 meter natin. What if, nung nagkaroon tayo ng bracing, nahati yung dalawa natin, so let's say, so we have 5.5 here, and dun sa kabila naman, this is 3.5. So, yung consider natin value ng L natin, yung larger value. Kasi, the more na humahaba yung column natin, mas nagiging critical siya. So, for this, we are going to use the value of your Ly, which is equal to 4.5. So, yung Ky, Ly, over Ry. Yung Ky natin, that is 1.0. Yung Ly natin, since mm tayo, kaya 4,500. Siyempre, gagamitin natin dito yung value ng Ry natin na 94. So, the value of your slenderness ratio with respect to y-axis is equal to 47.872. So, after sa y-axis, sa x-axis naman tayo. Siyempre, palitan lang natin yung subscript natin. Yung kx natin, 1.0. So, we have 4,500. Yung rx natin, dito sa properties is 156. So, the value of your slenderness ratio with respect to x-axis is equal to 57.692. So, for this one, gagamitin natin yung larger na value ng slenderness ratio natin. So, therefore, ito yung nag-govern. Ito yung gagamitin nating slenderness ratio na ipagko-compare natin sa value ng 4.71 square root of E over Fy. So, yung value natin dyan, that is equal to 113.403. And yung nakuha nating slenderness ratio na 57.692, and yung kakakuha pa lang natin na 4.71 square root of E over Fy. So, pagko-compare natin yung dalawa, since less than yung value ng slenderness ratio natin, therefore, we have a short column. So, kapag short yung column natin, so we have a value of FCR, which is equal to 0.658 Fy raised to Fy over Fe multiplied by Fy. So, bago natin makuha yung FCR natin, kasi kapag nakuha natin yung FCR, makukuha mo na yung nominal. So, bago mo makuha yan, you must compute first for the value of your Fe. So, let's solve for the value of your elastic buckling stress. So, kapag kino-compute natin yung elastic buckling stress natin, so, gagamitin lang naman natin yung Euler's formula. So, madali lang naman yung Euler's formula natin. So, that is pi squared E divided by the slenderness ratio squared. So, let's compute for the value of your elastic buckling stress. So, pi squared, yung E natin, that is 200,000 megapascal over yung slenderness ratio natin. We have, siyempre eto, 57.692 quantity squared. So, the value of your Fe is now equal to 593.06 megapascal. And siyempre, yun nga, so meron tayong two method to determine short or long yung column natin. So kung gagamitin natin yung Fe, yung nakuha nating Fe, we will just compare that to 0.44 Fy. So 0.44 multiplied by 345. So pagko-compare natin yung Fe natin to the value of 151.8 megapascal. Since Fe is greater than to 0.44 Fy, so we have a short column. So otherwise, long column tayo kung less than yung Fe natin. So makukuha na natin yung value ng FCR natin. So we have 0.658. Yung Fy natin na 345 raised to 345 all over yung nakuha natin na 593.06 multiplied by the value of your Fy. So the value of your FCR is now equal to 270.443 megapascal. So after computing for the value of your FCR, madali na lang yung next step natin kasi we will just multiply yung FCR natin to the gross section nung steel natin to compute for the value of your nominal strength. Let's solve now for the value of your nominal strength. So nominal strength is now equal to FCR multiplied by the area ng cross section natin. So for this one, we have FCR na 270.443 megapascal multiplied by 17,100. So the value of your nominal is now equal to 4,624.575 kilonewton. So ito kasi naka-ano tayo dito, naka-megapascal. Tapos ito naka-mm squared lang tayo. So yung makukuha natin dito is in newton. Tapos i-divide lang natin to into 1,000 para makuha natin yung kilonewton. So let us solve for the design compressive strength and the allowable compressive strength. Kapag design compressive strength, that is LRFD. Or yung design, word na design. So yung para makuha natin yung design strength, so multiply lang natin yung nominal natin to the reduction factor. Yung reduction factor natin dito, that is 0.19. And yung nakuha natin, so the value of your design compressive strength is now equal to 4162.118 kilonewton. And then for ASD naman, ito yung tinatawag nating allowable naman. Allowable compressive strength. So that is denoted by P sub E. So yung nominal na nakuha natin, we will just divide that to a factor of safety. Divide natin siya sa factor of safety na 1.67. So we have an allowable which is equal to 2769.207 kilonewton. So for this, nakuha na natin yung mga compressive strength natin sa ASD and LRFD. So yung P sub U natin dito, that is 4162.118. Yung allowable strength naman, that is 2769.207. Ngayon, ito yung capacity ng section natin na kaya niyang dalhin. So, we're going to compare that dun sa mga actual loads natin sa steel column natin. So, sinabi dito, we have a dead load of 600 kilonewton and a live load of 1,900 kilonewton as stated dito sa problem natin. So, siyempre, if we were going to compute yung sa LRFD natin, so we have two methods here. So we have LRFD and ASD. Kapag LRFD, kinukuha natin yung actual natin na loads na may mga factor tayo. So for this one, that is 1.2 dead load plus 1.6 live load. Kapag naman ASD, yung actual natin, that is only dead load plus live load na wala tayong mga factor. So, kunin natin yung P actual natin. So, we have 1.2, yung dead load natin na 600 plus 1.6 live load na 1,900. So you will have a P actual which is equal to 3,760 kilonewton based sa LRFD. Sa ASD naman, we have 600 plus 1,900. So your P actual, that is equal to 2,500 kilonewton. So this is our actual compressive strength. So yung nakuha natin mga compressive strength o yung capacity ng section natin, ipagko-compare natin sila sa mga actual loads natin. So for this one, dito muna tayo sa PU. So co-compare natin yung PU sa P actual natin dito. Yung PU natin, that is 4,000 plus. Compared natin siya sa 3,760. Therefore, greater than yan. Therefore, yung section natin is adequate siya. Next naman, sa ASD naman, yung allowable compressive strength, compare natin siya sa actual compressive force natin. So, that is greater than also. So, this is 2.7 tas 2.5 lang. So, therefore, adequate yung section natin. So, adequate yung section natin considering LRFD and ASD method.